What is the gut? The grand unified theory, what is known as the Holy Grail of Mathemagix, of mathematical physics. Okay, and here's, I guess, a rundown so that you can follow along. Okay, the gut, the Holy Grail of Mathemagix. Gut is what? The unification of light and gravity. You could also say it's the unification of quantum mechanics and general relativity. General relativity is the world of the big. We're talking about planets, stars, galaxies, and the big issue there is gravity. And then you have the world of the small, and that typically involves light and things like electricity, magnetism, which could also be applied, on a on a universal basis. Okay, so what is mathematical physics? It's equations followed by irrational mechanisms. Okay, not a single one of the mechanisms proposed by mathematical physics is rational. What is irrational? The movement of concepts. If you start vibrating the field, if you start waving the wave, right? If you start transferring energy or moving the mass, well, then it gets very, very dangerous, okay? So, we don't want to start moving concepts around. That's what they do. And so that's what they're trying to do. They're trying to merge light with gravity and general relativity with quantum mechanics. That's the Holy Grail. But what are they looking at? They're looking at an equation. They're trying to find this grand equation that underlies it all, that can describe it all. Because again, they're not talking about explanations. They're not talking about mechanisms and causes. What they're talking about is just a description, a numerical, a quantitative description. Okay? And that's what an equation does. It describes. That's all it does. So now let's say we have some entity out there. We'll call it what unidentified flying object. You like that one? A UFO? Okay? Its speed is 30 miles per hour. So what are we talking about? Are we talking about a turbo car? Are we talking about a galloping cheetah? Are we stretching a spring, a coil? You're looking at the front end of the coil. Is that what's traveling at 30 miles per hour? Or is it flowing water? Are we having a liquid flow there? And here, let me give you an example. Okay, here it goes. Okay, look at him. He goes everywhere. So what are we staring at? We're seeing what, a tornado there? What is that? So the first thing you need to identify is the thing that is moving. Unless you can identify the thing, what are you describing? Okay, this is the problem. And right now we don't have entities for the invisible, intangible mediators that Mother Nature uses out there. So the fact that you can tell me how fast your turbo car goes, or your galloping cheetah, or when you stretch a coil, it doesn't tell me which of these you are referring to, because the equation applies equally to any of those situations, in any of those contexts. So the issue is there, that you need to identify the invisible, intangible entities that Mother Nature uses. And that's what they've never done in mathematical physics. That's why we don't have explanations of mechanisms today. What we have is equations, we have descriptions, we have predictions, but we don't know what's causing it. And for 3,000 years, people have asked the same question. What causes gravity? A little sooner than that, what causes magnetism? What causes electricity? I mean, what was Faraday investigating? What was Maxwell investigating? They were trying to figure out how this universe works. And by how, I don't mean a description like saying, oh, it works at such and such speed, or this is the acceleration, or whatever. No, they were trying to figure out what causes it. What are we staring at? Why does a pen fall to the floor? That's what they were trying to figure out. What causes that to happen? And here, let me give you a good example. Here we have the lines of force of a magnet, okay? And they say, well, this is what we call a magnetic field. Magnetic field is made out of all these lines of force, as Mr. Faraday told us. And so when you look at this, they say, they try to explain that. They say, well, those lines of force don't really exist. We use them just to give you some sort of physical interpretation of what's going on there, but they're not really there. So you have all these iron filings, they line up around the magnet, and they form those familiar patterns. And they say, well, don't pay attention to that, because those lines of force are not really there. And so you say, well, why does a magnet attract another? And they start talking about the field. They start vibrating in this concept. What is a field? It's a bunch of values, okay, that get weaker and weaker as they get radially away from ground zero. Okay, so we call that a field. And now they're going to vibrate these numbers, and they say, well, these fields vibrate. And even with that, they cannot explain attraction, because tell me how that magnet attracts the other one. That's what I want to know. Okay? And so when we go and we look up Mr. Faraday and Mr. Maxwell, this is what they tell us. This comes from Faraday on the physical characters of the lines of magnetic force. That was from 1852. He obviously was investigating magnetism since the 1830s at least, not earlier. And he says, I cannot conceive curved lines of force without the conditions of a physical existence in that intermediate space. What was Mr. Faraday saying? There's something there that I cannot identify. It was a little too early for that, right? Bgaede wasn't born then. And so he was trying to figure out what was in that space. What did Mr. Maxwell say? He put this in his book, A Dynamical Theory of the Electromagnetic Field. He knew what a field was that region where something is occurring, but he says the following, field, this is his definition, okay? The space in the neighborhood of the electric and magnetic bodies. In that space, what? There is matter in motion. Matter in motion. A field is a region where there is matter in motion. It's an exotic type of matter, no doubt about it, but it's in motion. And you say, well, Bill, is that really true? Is there something moving in a field? I mean, the iron filings don't seem to move. They just stick to the magnet and there's nothing moving there. So what do you mean there's something moving in that region of space like Mr. Maxwell said? Okay, and here, let's prove it. You want truth, proof, evidence? Okay, let's do an experiment here. Here we put a magnet underwater. We're going to put a magnet underwater, and you can see that each one of the iron filings is drawn individually one by one. There is something moving in that region called field, magnetic field. Here it is. Okay, look at that. Okay, you can see the iron filings being pulled one by one towards the magnet. Something is twirling, something is moving in a region around the magnet, and we call that region. We refer to that region as a magnetic field, but a magnetic field is not a static thing. Okay, what it is, like Mr. Maxwell said, there is matter in motion. Matter in motion. You cannot avoid it. Okay, so what we need to do is identify what is that Mother Nature uses, because we're going to unify, remember, electricity with gravity. We're going to try to figure out, because what is electricity, what is magnetism? Well, we have electromagnetism, and electromagnetism, as according to Mr. Hertz, is what builds the electromagnetic wave known as light. So we have light and gravity, and we have to include electricity and magnetism within that context, okay? And so here's an experiment that will, in addition, unify quantum mechanics with general relativity, because general relativity, again, is the world of big. Quantum mechanics is the world of the small. Okay, we have the lunar ranging experiment, done for many years. The project was shut down afterwards, a couple of years ago, I think. Here's the lunar ranging, okay? And you have what you have. You have a laser pointed from the Earth to a retroreflector on the moon. Okay, let's do it with waves. Okay, here we have the electromagnetic waves. What are you staring at? You're staring at vectors that are moving. What is a vector? Well, vector is just magnitude and direction. What are we talking about magnitude? A number. So you're talking about 5 whatevers, and they're moving in a given direction. That's what those arrows represent. A whole bunch of arrows makes a field, and a field makes light. In other words, this laser made out of light, you're talking about vectors. So what are we talking about? We're talking about numbers. This is a quantitative description of what light is. It doesn't tell us what light itself is. Okay, let's do it differently. Let's do it with particles. Here we go with particles. Okay, so we go with particles. How are you going to unite? Because remember, the grand unified theory is about unifying light with gravity. Okay, we got light. How do you unify that with gravity? I mean, how does those particles that go from the Earth to the moon and back after they hit the retroreflector, how does that produce pull? How does that produce for the moon not to leave the solar system? That's the question you have to answer. Okay, and there's a bigger problem also with particles, in case you want to simulate light with particles, the laser with particles, and that's the fact that the moon is moving. See, if the moon was standing still, well, you can maybe still say, I shoot particles at the retroreflector, they bounce off, they come back to Earth. Great. Now let's move the moon. We're going to be moving the moon now. Okay, here it is. And this is what happens to the particles. The particles are going to have to describe a curve in space. Okay, you can see how that goes. As the Earth moves and moon moves, you have to shoot the particles where the moon is going to be in the next few seconds. Okay, see it here? We got 384 kilometers, 1,000 kilometers. That's almost 1.5 light seconds. Okay, so round trip, you're talking about almost 3 seconds. And by that time, the Earth is traveling 30 kilometers per second around the sun. The moon is traveling 1 kilometer per second around the Earth. Those are the speeds. And so you describe a curve. So here you're shooting these particles at the retroreflector. They have to trace a curve through space in order to hit the reflector to where the moon is going to be in 1 second, 1.5 seconds really, and then it bounces back and to where the Earth is going to be in 3 seconds later. Yeah, sure. What is this, ping pong? Okay, you see the problem. You got to shoot the particles where the moon is going to be, even if it's just a relatively short distance. Again, you're not supposed to point it directly at the retroreflector. That's my point. Okay, so this is the problem with that. Okay, that with particles. But again, even if you use particles or waves, that's great for light. Now unify that with gravity, because that's what the gut is. The gut is the grand unified theory. Okay, and so here we do it with ropes. This is the way science does it, rational science. Okay, we have the laser there. And what you have is actually ropes. We put only one rope. Obviously, we're talking about gazillions of ropes here. But we put one rope, and you can see what's happening. Nothing goes anywhere. All you have is a rope tying your laser directly to the retroreflector and back. All it does is twirl in place. We receive the signal at the atom that receives the thump. Okay? And what happens? Well, let's move the moon around. What happens when we move the moon now? Well, you can see what happens. You have all these ropes, electromagnetic ropes, twined threads. Every atom from the moon is connected to every atom of the Earth. And so both of them can move anywhere they want. Light will never get lost because light can only travel along a rope. What is light? Just a torsion of the rope. It's not even any traveling. That's why it's so fast. You know, just twirl a rope in place and you'll find out that the signal travels, you could say, instantaneously. That's how fast light is. 300,000 kilometers per second. You can only explain it with something like a rope. Okay, a twined pair of threads, a DNA-like rope. Then you can explain the speed. Okay, so here we have an astronaut, and he's falling to Earth. Okay, here he goes. He's falling to Earth. How are we going to explain this? And again, remember that you not only have to explain it, you have to do two things. You're going to be uniting light with gravity. Okay, here we have gravity. You say, well, he falls to Earth because of gravity. Great. We have no explanation. All we have is a description. We're saying that's gravity that did it. Okay, so let's do it with force, which is what quantum mechanics would propose. You know, that's what Newton proposed. He says there's a force. Okay, so let's go with the force. Here's the force. Force is pushing him down. So we have a concept called force, and it's pushing the astronaut down towards the Earth. Great. We're going to learn a lot with that. The word force. You know, all you can do with force is describe. You have an equation. You say force is equal to gravitational constant G times mass divided by distance squared. That's just a description, a quantitative description. So far, you haven't explained anything. So by saying force, you're only giving me a mathematical description. Okay, let's replace that now with particles. How do we do it with particles? Here's the astronaut being pushed by particles. Great. So we have all these particles everywhere. What's the mechanism? And even if you have a mechanism, you can tell me how the astronaut being, for example, pushed by all these particles. Tell me how that relates to light. Because remember, you have to unify light with gravity. We have gravity, but where's the light? Okay, so that's the problem there. How do they do it in general relativity? Well, there it's a little scary, okay? Here it is. Okay, we have warp time, okay? And there you have warp time. Okay, the guy, I guess, slides down that canvas. Bumpy ride there, okay? What the hell is that? How do you explain that the astronaut falls to Earth because, you know, there's this canvas made of time and it's waving around because you have to have waves. Remember, you have to have gravitational waves. How does that relate to anything? And there you have the waves, okay? How do we do it with ropes, with science, with the rope hypothesis? Very simple. Every atom in the of the astronaut is bound to every atom on Earth. As he gets closer to the Earth, the ropes fan out. Period. We're done. Baby stuff. You don't need to go to college to understand this. Well, unless you've been brainwashed by the system. But otherwise, if you were an 8-year-old boy, you would say, well, I understand this. It's straightforward. You know, every atom in his body is connected to the Earth. As he gets closer, the ropes fan out. That gives you the acceleration known as gravity here on Earth. Obviously, on the moon, you would go at a different rate and so on, in the sun as well. Okay, so you can see the comparisons between the establishment and what we propose here. Here's another one. Here's the spoon. We let go of the spoon. Now we're on Earth. We're no longer out there in space. So we're going to be looking at quantum mechanics, or you could say classical mechanics, if that's what you vouch for, okay, what you defend. Here we have a spoon. It falls to the floor, okay? So we say, why did that spoon fall to the floor? Okay, so what are we going to do? Use green pixies, as this fellow suggested? We're going to have all this green pixies push the spoon downwards. And then what do we do with the green pixies on the other side of the planet? When the Chinese man lets go of the spoon, the pixies move in the opposite direction? I mean, this is kind of very specific. You're saying here it does, but then how does it do it on the other side of the planet? Okay? How did we do it in science? Well, very simple. If every atom of the spoon is bound to every atom on Earth, as the spoon falls to the floor, the ropes fan out. See how easy it is to understand the mechanism. Now, whether you believe in this or not, that's your personal opinion. What we're saying here, I'm giving you a mechanism that you can sink your teeth into. The other ones can't give you a mechanism. And that's why mathematical physics doesn't deal with mechanisms and dismisses them as what? As philosophy. Okay, so here's what you got to do. This is your homework. Okay, if you want to do the GUT, the grand unified theory, this is what you're tasked with. You have to unify particles with waves. What are waves? A bunch of vectors that are moving. Very scary stuff. What is a vector? Magnitude and direction. And they have these magnitude and directions moving sideways, perpendicular to the direction of the vectors. And there you have particles. You can assume that they're anything. You can assume that they're electrons, if that's what you want, photons, virtual photons maybe, tachyons, whatever you want to put in there. I don't care. Please unify these two proposals. How are you going to unify it? And so what they do is they elude the visualization because they cannot even visualize it. In fact, for the wave packet, who was it? Roger Penrose, Nobel Prize. What did he draw in his book? 2 books, by the way. He drew a corkscrew because he had no idea how to illustrate a wave packet. Okay, just a bundle of energy. But this is what you got to do. You have to unify the particles with the waves. Is there something you can do there physically? Absolutely not. Mathematically, which is the equation they're searching for, well, I don't know. I mean, first of all, we don't care, even if they find an equation, but I doubt very much you can find an equation that can unify first the particles with the waves, and then gravity with light. In other words, quantum mechanics and general relativity. Okay, how do we do it in science, in real science? Well, here you have it. Let me put it over here. See how easy it was? There it is. You have 2 atoms. They're bound by what we call the electromagnetic rope, a DNA-like mediator. And what it does is it twirls around. It torques. And it's these torsions that thump the atoms to which they're connected. And you receive the light that comes from the other atom, and the other guy receives the light that comes from your atom. That's what's happening. That's why it's almost instantaneous when that happens. Okay? Okay, and so give me a second here. Give me a second. I'll be back in a second. Okay, I'm back. This is what we are trying to do here. We're trying to unify in mathematics, right? What they're trying to do is unify Newton's gravitational equation together with Einstein's field equation. Okay, this is essentially what it is for gravity. Even if you could unify those, you could say that Newton's gravitational equation is Einstein's equation at the limit when it stands still, when everything's standing still. Okay, but that can be done. Okay, but look at the mechanisms. What does Newton propose? Well, he suggested force, and he mediated that in his mind with particles. On the other hand, look at Einstein. What did he propose? Warp time. And I'm not sure how you can unify warp time with particles. Okay, that's the problem there. So the unification of the equations could be one thing that might be achievable. What you cannot achieve is the unification of the mechanisms. And then unifying this with light. Well, good luck with that one. Both from the point of view of equations, which at least quantum mechanics has been unable to do, but for sure you cannot unify light with gravity out there in space. I mean, what you're going to have to do is explain why the Earth doesn't fly out of the solar system because it's held by what we call gravity to the sun. What's that got to do with light? And that's where the problem is. They cannot unify these two mechanisms to begin with, let alone the mathematical description. And here we have another problem we're going to throw on top of that because you have the gravity waves. Okay, remember a couple of years ago they proved that 2 black holes collided and they were able to pick up the gravity waves from those 2 black holes. The waving of what? And then this is the issue. The issue if gravity is made of waves, of some kind of waves, how does that pull if a wave is an outward mechanism? I mean, a wave is, you throw the stone in the pond, the waves, the ripples go outwards from where the stone fell. And so let's throw 3 stones in space. Here we go. Okay, here's the stones from the black holes, right? We'll call those the stones. And they create these waves, and the waves move outwards. But then you have waves moving out from another pair of black holes and from another black hole. So these waves move outwards. Please tell me, please explain to me, give me a mechanism of how these waves that go outwards pull on each other. How do these waves from one pair of black holes there pull on the waves created by another pair of black holes? In other words, how do they pull on the other black hole? They're all going outwards. So the mechanism is irrational, totally irrational. You cannot visualize this. So whatever they proved, NASA again, or all these groups that are out there, these think tanks, they go out there and they say, look, we've proven it. We were able to detect gravitational waves. Yeah? So those were the waves coming towards us. How do those pull us? How do you know they're gravity waves? That's the issue. And so, mathematical physics does not have mechanisms. And so the question is, if they're describing something out there, how valid is their description if they don't know if it's a bird, a plane, or Superman? I mean, first you got to determine that before you can, put an equation to it. To have just a value and say, look, we know how fast it goes, but we don't know what it is that's moving. Maybe it's the Tasmanian devil that I showed earlier. Okay, maybe that's what's moving. You got to identify that first. Okay, so here are the problems, with grand unified theory, and it's the grand unified mechanism the problems theorists must solve, at least from a physical point of view. That's what we talk about here. First, we have to distinguish between explanation and description. We have to distinguish between mechanism and equation. Equation is just a description, a quantitative description. A mechanism is something that you can just watch. You want to know how the window broke. Okay, you see the stone go through the window, we're done. We know how the window broke. That's what we want to see, something as simple as that. Kindergarten stuff. That's what Mother Nature understands. Mother Nature never went to school. She never learned math. We invented the math as a description, a language of descriptions for what Mother Nature does. And the only thing we can describe is, what we can see. We cannot describe or, quantify that which we cannot see. So we need to know, what's in that invisible world. That's what we need to detect, elucidate. And so what's the problem? The issue is that you have to explain action at a distance, specifically in the case of both magnetism and specifically gravity. Okay, action at a distance. Are you going to do it with particles? Because this is what quantum mechanics uses, even though the particles of quantum mechanics ain't particles. The particles of quantum mechanics are wave function collapses. That's what they are. They have a wave function collapses, it turns into a particle. And they call that a particle. So it's a concept that collapsed. And good luck with that one. No wonder they haven't incorporated gravity into the standard model of quantum mechanics. Waves, waves are outward mechanisms. But what are waves? They're a bunch of vectors. So I guess that's the end of that. I mean, you cannot explain a physical mechanism with outward going waves, and for sure you cannot explain attraction with waves going outwards. And then you have the rope. So that's something for you to consider. If you want to pull on the donkey, you better have an elongated entity, a mediator between your hands and his neck. Okay, so I don't care if you use a rod, I don't care if you use a chain, coaxial, wire, whatever you want to use, but it better be elongated. It must reach from your hands all the way to the donkey. Then you can explain pull. If you do not put a mediator, you are, in effect, right, doing black magic. You're explaining with black magic. You're saying that you move here, your hand, and somehow, by remote control, the donkey moves towards you. Yeah, sure. And so, you have to reconcile waves with particles. You have to reconcile push with pull. That's what essentially the gut is. And again, you can't do it with one-way mechanisms because they don't attract. And you have to deal with, especially, intangibility and invisibility. Your task is to determine, to tell me what it is that is in that space between your hand and the donkey, between the earth and the sun, between the earth and the moon, between the Andromeda galaxy and the Milky Way galaxy. Why are we pulling on the Andromeda galaxy? How are we doing that? What is the mechanism? That's the issue. And if you can figure that out, hey, you get a Nobel for discovering the gut. Okay, because that's what the goal is. That's the Holy Grail, the grand unified theory of Mathemagix.